The universe was supposed to begin slowly. First came darkness, then the earliest stars. Only much later should enormous galaxies and tightly organized structures have appeared. But the deeper we look, the less certain that timeline becomes. Light from the edge of the observable cosmos is revealing objects that seem far too developed for their age. They are brighter, denser, and more chemically complex than many earlier models expected. Some may simply be rare exceptions. Others may expose gaps in how we understand the first stars, the growth of galaxies, and the invisible matter surrounding them. And a few observations have inspired ideas far more radical than anything astronomers are ready to accept. None of this proves that modern cosmology is wrong. It does mean that the young universe may have been far more active than we imagined. The James Webb Space Telescope is not only seeing farther into space, it is watching the first chapters of cosmic history become less predictable with every new discovery. Subscribe to The Last Signal for more calm documentaries about space, science, and the questions that remain open. Because the farther we look into the beginning, the more mature the universe appears. In the beginning, the universe contained the raw ingredients for structure, but almost none of the finished forms visible across the sky today. Ordinary matter was dominated by hydrogen and helium, with only tiny traces of anything heavier. There were no developed galaxies, no crowded clusters, and no long history of stars producing the elements that later worlds would need. Gravity had plenty of material to work with, yet it also needed time. Dark matter provided the first hidden framework. It gathered into invisible concentrations, creating gravitational wells where ordinary gas could collect, much like rainwater settling into the lowest parts of uneven ground. As more gas accumulated, the densest regions compressed until the first stars ignited. These stars were probably hot, short-lived, and far heavier than most stars shining today. They burned through their fuel rapidly and altered everything around them. One by one, isolated lights appeared inside enormous stretches of blackness. There were no familiar constellations and no spiral galaxies filling the distance. Each star stood inside a reservoir of neutral gas that absorbed much of the energetic light trying to escape. Ultraviolet radiation then began stripping electrons from that gas, making more of space transparent. Astronomers call this process reionization, the long period when the first starlight gradually cleared the cosmic fog. The darkness did not disappear at once. It retreated unevenly, region by region, as more stars and young galaxies switched on. Those first stellar generations also began changing the chemistry of the cosmos. Deep inside them, hydrogen and helium fused into heavier elements. When the largest stars died, they scattered part of that processed material into surrounding space. New stars formed from gas that was no longer chemically untouched. This cycle had to repeat before galaxies could contain richer mixtures of carbon, oxygen, nitrogen, and other elements. The standard picture therefore describes cosmic growth as a gradual accumulation of matter, light, and chemical history. Small dark matter concentrations gathered gas and produced stars. Those regions merged with others, drawing in more material and creating larger galaxies. Continued gas inflow and repeated mergers allowed some systems to become far more substantial. The process resembled towns expanding into cities, because complex structures generally required smaller ones to combine, grow, and reorganize. Galaxy clusters represented an even later level of development. A cluster is not simply a collection of bright galaxies appearing close together in an image. It is a deep, gravitational system containing hundreds or even thousands of galaxies, extremely hot gas, and far more dark matter than visible matter. The galaxies are only the illuminated part of a much broader structure. Between them lies thin gas heated until it shines mainly in X-rays. Around and through the whole system, dark matter supplies most of the gravity holding everything together. Assembling such an environment requires a tremendous quantity of matter to gather into one region. It also requires smaller systems to interact, merge, and settle into a shared gravitational arrangement. That is why large clusters are usually treated as advanced products of cosmic construction rather than first-generation objects. None of this means the young universe had to be empty or uniform. Gravity can work quickly where matter begins unusually concentrated. Some galaxies could become luminous and heavy much sooner than average, especially in rare regions with favorable conditions. The standard model has always allowed exceptions. The prediction concerns how many such exceptions should exist, how substantial they can become, and how often surveys should find them. An isolated object may fit comfortably within statistical expectations. A large population of highly organized systems is harder to explain, because each one uses part of the limited time and matter available during cosmic dawn. The same distinction applies to clusters. One unusually dense system might be a rare outcome that the model already permits. Many comparable systems appearing at similar distances would suggest that structure assembled more efficiently than expected. The question is not whether gravity could create something large in the young cosmos. The question is whether it could do so often enough to match what telescopes are beginning to reveal. Rarity, not absolute impossibility, is the real test. Faint arcs curve around a distant concentration of matter, while blurred smudges appear stretched into shapes no galaxy would naturally take. These distortions mark XLSSC 122, an exceptionally distant galaxy cluster seen as it existed a little over 3 billion years after the Big Bang. At first glance, the image shows only scattered points and elongated patches of light. The real structure is much larger than the visible galaxies suggest. Its importance comes from the amount of matter already gathered into one region, when the cosmos was still comparatively young. Seeing a dense system so far back in time therefore raises a precise question. How could so much matter assemble into one gravitational environment so quickly? Most of the system's mass does not shine or reveal itself directly through ordinary telescopes. Astronomers infer that hidden component by studying what its gravity does to light passing behind it. According to general relativity, a sufficiently massive object changes the paths followed by nearby light. Background galaxies that would normally look compact can appear elongated, duplicated, or bent into thin arcs. The distant structure acts as a gravitational lens, though it is nothing like a polished piece of glass. The combined gravity of galaxies, hot gas, and dark matter alters the geometry through which the light travels. One faint streak may curve around the center. Another may appear twice on opposite sides. Small blue fragments can sit beside reddish smears, each representing light that crossed a different route before reaching the telescope. Nothing in the image labels where the hidden mass begins or ends. Researchers measure the positions and shapes of background sources, then compare them with models of how different mass distributions would bend the same light. Step by step, they create a map of the gravitational field. The method resembles working out the form of an unseen object from the marks it leaves around it, except the evidence comes from curved light rather than an ordinary shadow. Through this process, gravity weighs what the eye cannot see. The reconstructed map indicates that most of the cluster's gravitational mass belongs to dark matter. The bright galaxies contribute only a fraction. Hot gas spread between them adds more ordinary matter, yet it still cannot account for the strength of the lensing signal. A compact central concentration of dark matter makes the system appear especially organized for its age. That does not mean it had reached the same condition as every massive cluster in the nearby universe. Its galaxies, gas, and internal motions may still have been evolving. The key issue is statistical. The standard cosmological framework allows rare regions to begin with slightly higher concentrations of matter than average. Gravity amplifies those differences over time. A region that starts denser can collapse earlier, attract more gas, and become a meeting point for surrounding galaxies. In a vast enough universe, unusual systems should sometimes appear. Finding one does not automatically expose a flaw in the model. Its significance depends on how accurately its mass has been measured, and how uncommon such a mass should be at that cosmic age. Lensing estimates carry uncertainties because researchers must account for the unknown shapes and distances of background galaxies. Different assumptions about the system's geometry can also change the reconstructed mass. Material along the same line of sight may strengthen the signal even if it does not belong to the central structure. Survey selection introduces another complication. Astronomers are more likely to notice dense, conspicuous clusters than ordinary ones that produce weaker signals. The first discoveries, therefore, do not form a perfectly neutral sample. They are drawn toward the most visible examples, much as a distant mountain range first reveals its highest peaks, while lower ridges remain hidden. This effect can make the young cosmos look more heavily populated, with extreme systems than a complete survey would show. None of these cautions erase the observation. They define the work needed to understand it. A well-calibrated mass estimate can be compared with simulations that predict how often clusters of different sizes should exist at different cosmic ages. If the system falls inside the rare but permitted edge of those predictions, it becomes an impressive outlier. If repeated surveys reveal many similar clusters, the interpretation changes. Their combined abundance would suggest that large structures gathered sooner or more efficiently than the models expected. That is why one early cluster acts more like a warning light than a final verdict. It tells researchers where the timeline is under pressure, but not yet whether that pressure comes from measurement, rarity, or missing physics. A single outlier can live at the edge of a model. A population begins to test the shape of the model itself. In a crowded field of infrared light, MOMZ-14 first appeared as little more than a weak point among many others. To human eyes, it would have been completely invisible. Its light had traveled for almost the entire age of the cosmos, and cosmic expansion had stretched that light far beyond the wavelengths people can see. The object did not announce itself as a record. It had to be separated from noise, foreground sources, dust-reddened galaxies, and the limits of the detector itself. That first step depended on color. Astronomers observed the same patch of sky through several infrared filters, each one acting like a window that admitted a different portion of the incoming light. The source appeared clearly in some filters, and then disappeared in those sensitive to shorter wavelengths. This pattern offered an important clue. Light at those shorter wavelengths had been absorbed by hydrogen lying between the galaxy and the telescope. The point where the signal dropped away revealed how far the light had been stretched during its passage across the expanding universe. Researchers call this a dropout because the source seems to vanish when viewed through certain filters. The method is powerful, but it does not prove distance by itself. A nearer galaxy covered in dust can look unusually red. A random fluctuation in the image can imitate a faint source. Strong emission from a closer object may also create colors that resemble something much farther away. Imaging, therefore, produces candidates, not final answers. The crucial test comes when the same faint light is passed through the James Webb Space Telescope's near-infrared spectrograph. Instead of recording the source as one blurred point, the instrument separates its light into individual wavelengths. A single glow becomes a narrow record crossed by rises, gaps, and abrupt changes. It is similar to taking one musical chord and separating it into its individual notes. Each part carries information that was hidden when all the light was blended together. In the darkness surrounding the telescope, no sound accompanies this process. A mirror gathers photons that left their source when the cosmos was only a few 100 million years old. Those photons are guided into the instrument and arranged by wavelength with extraordinary precision. What arrives as a barely detectable trace is spread into a pattern that can reveal distance, chemical content, and the physical conditions inside a remote system. The spectrum is not a photograph of the past. It is a measured imprint of how matter interacted with light before that light began crossing space. Astronomers search the pattern for recognizable features produced or absorbed by atoms. Cosmic expansion shifts these features toward longer wavelengths. The greater the shift, the farther back in cosmic history the object is being observed. Redshift describes the size of that stretching. No equation is required to understand the basic idea. If the same atomic feature appears much farther toward the infrared than it would nearby, the light has crossed an expanding universe for an exceptionally long time. For MOM Z14, the measured shift lies above 14. That places the galaxy roughly 300 million years after the Big Bang, among the earliest spectroscopically confirmed systems reported at the time. The time span sounds large in human terms, yet it represents only a small opening chapter in cosmic history. If the full age of the universe were compressed into a single calendar year, this light would come from the first days of January. Stars, galaxies, and chemistry had only recently begun changing the darkness. The surprise is not simply that matter had collapsed into a visible object. The source was luminous enough to be detected across an almost unimaginable distance. That brightness suggests that intense physical activity was already taking place inside a remarkably compact region. At the same time, a distance record must be handled carefully. New observations can push the boundary farther. Revised calibrations can change how a spectrum is interpreted. Another candidate may later receive stronger confirmation and replace the current holder. Records are temporary because the observational frontier is still moving. The spectroscopic method matters more than the title of earliest known galaxy. It transforms a persuasive color pattern into a measurement grounded in recognizable features of light. It also allows researchers to separate what the telescope truly recorded from what models infer about the source. Distance is one result. Brightness, size, stellar mass, and chemical composition require additional assumptions. Even a confirmed redshift does not explain why the object shines so strongly. It only establishes when the observed light began its trip. That distinction is essential. Finding a galaxy at the edge of sight answers the question of where it belongs in cosmic time. It leaves the harder question untouched. What could make such a small and ancient system visible from so far away? Momsey 14 was too bright and already enriched for such a small object from such an early period. It appears to be only a few hundred light years across, yet it releases an astonishing amount of radiation for such a compact system. By comparison, the Milky Way stretches roughly 100,000 light years from side to side. Physical size alone, therefore, cannot explain what the telescope records. A small galaxy can shine far beyond its weight if most of its output comes from young, massive stars. These stars burn hotter than older populations, and they consume their fuel with exceptional speed. A brief burst of star formation can make a modest system look far more powerful than its total mass would suggest. It is like a small building with every window blazing, while a much larger structure nearby remains mostly dark. The apparent brightness tells astronomers that intense activity is taking place. It does not immediately reveal how much matter is present. One possible explanation is that the source was producing new suns at a furious rate. Dense gas may have collapsed into clusters where many high-mass objects ignited within a short interval. Because such bodies release tremendous ultraviolet energy, even a relatively small population can dominate the total output. Another possibility is that this stellar population differed from those commonly observed nearby. The first generations may have contained a larger share of heavy objects, creating more radiation for every unit of material. Current estimates also leave room for an actively feeding black hole near the center. As gas falls towards such an object, it heats and radiates before crossing the point from which nothing can return. That process can add considerable luminosity without requiring the surrounding galaxy to contain a vast population. The black hole is not a ready-made answer because researchers still have to separate its contribution from the surrounding stellar glow. Gravitational magnification may also influence the measurement if foreground matter strengthens the signal, reaching the telescope. Several effects could operate at once. The deeper surprise comes from the spectrum. The reported pattern may indicate an unusual relationship between nitrogen and carbon inside the gas. At this distance, chemical measurements remain difficult, and every interpretation depends on faint spectral features and models of the source. Even so, nitrogen carries special importance because it usually points to earlier stellar processing. The young cosmos began with almost none of it. Earlier generations had to manufacture nitrogen from lighter material and later return it to space through winds, eruptions, or violent deaths. That enriched gas could then become part of another generation. Chemical development, therefore, requires more than one act of formation. It requires matter to enter a star, emerge altered, mix with surrounding gas, and rejoin the cycle. The process resembles raw material moving through a series of furnaces, with each furnace changing what the next one receives. In a nearby system, such recycling can unfold across vast spans of time. Here, the same sequence may have taken place within only a small fraction of cosmic history. Picture the interior of this confined environment. Scorching stellar bodies crowd regions filled with thick gas. Powerful radiation presses outward while gravity keeps drawing material inward. Stellar winds carve cavities through the surrounding clouds. The heaviest objects exhaust their fuel quickly and end in explosions that send processed elements back into their surroundings. New pockets of gas cool, collapse, and ignite again. The environment would not be calm or evenly organized. It would be a compressed cycle of birth, radiation, collapse, and chemical change. Some ancient globular clusters show abundance patterns that also contain unusually high nitrogen compared with carbon. Globular clusters are tightly packed, old groups containing many stars within a relatively limited volume. The resemblance is intriguing because it suggests that similar chemical pathways may have operated very early. It does not prove that a present-day type of globular cluster already existed in the same form. Different physical environments can sometimes produce comparable chemical signatures. The evidence may instead point to a short-lived population that processed gas with unusual efficiency. Researchers must also consider whether an active black hole, uncertain temperature, or assumptions inside the spectral model affected the inferred nitrogen signal. The interpretation remains open, yet the central pressure does not disappear. A diminutive object appears to have produced intense luminosity and possibly recycled material through earlier generations. If those measurements hold, the problem is not simply how the first stars appeared. It is how quickly their products could be returned, mixed, and used again. The young universe may have operated less like a slow beginning and more like a highly efficient stellar engine. Matter was already carrying the chemical record of lives that had begun and ended before the observed radiation started crossing the cosmos. A wide Webb survey field contains far more than one remarkable object. Scattered across the infrared image are dozens of faint candidates, each representing a possible galaxy from the first several 100 million years of cosmic history. Most are barely visible. A few stand out strongly enough to attract immediate attention. Those conspicuous sources matter, but they can also distort the first impression of the population around them. The James Webb Space Telescope has revealed multiple candidate and confirmed galaxies from periods once expected to contain far fewer luminous systems. The repeated appearance of these objects is more important than any single distance record. A record can be an extreme exception. A pattern asks whether the underlying assumptions are incomplete. Even then, the first estimates are not always the final ones. Many candidates were identified from broad filter images before detailed spectra became available. In those images, all the light entering a filter is combined into one measurement. Strong emission lines can add substantial energy to that band and make a source appear heavier or older than it truly is. The extra output may come from gas energized by a relatively small number of powerful young stars. Once spectroscopy separates the signal into narrower wavelengths, researchers can identify that contamination and revise the inferred mass. Dust creates another layer of uncertainty. It absorbs some wavelengths, releases energy at others, and can make a closer or younger system look redder than expected. An active galactic nucleus can complicate the picture further. This is the intensely radiant region surrounding a feeding central black hole. Its output may dominate an entire galaxy, even when the surrounding stellar population is comparatively modest. If researchers treat that glow as starlight, they can overestimate how much mass has accumulated. A galaxy's luminosity is not a simple scale placed beneath its mass. Young massive stars release far more light for each unit of material than older, cooler populations. A brief burst can temporarily turn a lightweight system into one of the most visible objects in its field. The first stellar populations may also have contained a larger share of heavy stars than nearby examples, increasing their light without requiring equally large stellar masses. Gravitational lensing adds another complication. Foreground matter can magnify a remote source, while small differences in the lens model can change the reconstructed properties of the object behind it. The faintest ordinary members of the population present a different problem. They often remain below the telescope's detection threshold. A survey can only count what produces enough signal to rise above the background. Picture a distant city hidden beneath heavy fog. Only the tallest illuminated buildings can be seen from far away. The low houses, dark streets, and ordinary blocks remain invisible, even though they may contain most of the city. Astronomers face a similar limitation when observing the earliest galaxies. The first detected members are naturally the most radiant, unusual, or magnified examples. Judging the whole population from those sources alone would make the young cosmos seem dominated by extremes. This selection effect does not make the surprising objects unreal. It means their abundance cannot be measured by simply counting the most dramatic images. Researchers must estimate how many dim systems escape detection and how often magnification lifts an object into view. Conventional physics still offers several ways to soften the apparent conflict. Gas may have cooled and collapsed more efficiently in some early dark matter halos. Star formation may have arrived in sharp bursts rather than at a steady rate. Feedback from radiation, stellar winds, and black hole activity may have behaved differently in dense primordial environments. The broad cosmological framework could remain intact, while the detailed physics inside young galaxies requires substantial revision. That possibility should not be mistaken for an explanation already proven. Some confirmed sources remain difficult to reproduce, even after more cautious assumptions are applied. The issue can only be settled by moving beyond isolated examples. Complete samples must distinguish candidates from spectroscopically confirmed systems. Repeated spectra must separate stellar output from glowing gas and central black hole activity. Lensing models must recover intrinsic brightness rather than the amplified signal seen from Earth. Only then can astronomers compare the observed number of early galaxies with the populations predicted by simulations. Surprise becomes a true test only when the unusual objects can be counted, weighed, and placed within an unbiased sample. Cosmology and galaxy formation are related, but they are not the same model. The first describes the broad universe, its expansion, its overall matter content, and the way structure grows from small initial differences. The second describes what happens inside that framework when gas cools, stars ignite, black holes feed, and radiation pushes material around. Those two levels can disagree in detail without the entire picture collapsing. The standard cosmological model sets the size and rules of the building site. Galaxy formation describes the machinery, the workers, and the weather operating inside it. If the machinery behaves differently from what engineers expected, the site itself does not automatically stop making sense. This distinction matters because the most uncertain parts of current simulations involve ordinary matter. Researchers call this baryonic physics, meaning the behavior of gas, stars, dust, radiation, and black holes. Gravity is comparatively simple to calculate across very large scales. Gas is not. It can cool, heat, collapse, fragment, become turbulent, form stars, absorb radiation, and be thrown outward again. Each process can alter the others. A simulation may track dark matter with enormous precision while still approximating what happens inside a cloud far smaller than the smallest detail it can resolve. Picture an enormous digital volume beginning almost smooth. Slight variations run through it like shallow ripples. As gravity acts, thin filaments emerge and intersect. Dark matter gathers into halos, and bright knots appear where gas falls into the deepest regions. From a distance, the evolving web looks clear and orderly. Inside each luminous knot, however, the calculation reaches scales too small to follow directly. Researchers must insert simplified rules for how quickly gas becomes stars, how explosions return energy, and how central black holes affect their surroundings. Those rules are not arbitrary, but they are still approximations. A small change in them can produce a large change in how many bright galaxies appear at cosmic dawn. Feedback is one of the most important examples. When new stars release radiation and later explode, they can heat nearby gas and push it away. That slows future star formation by removing the material needed to make more stars. Under different conditions, the same pressure can compress neighboring clouds and help trigger fresh collapse. Black hole feedback can also either clear gas from a central region or stir and heat the material around it. The net effect depends on density, temperature, geometry, and timing. If early galaxies held gas more efficiently than expected, they could form stars at a faster rate without requiring a new expansion history or a different beginning for the universe. The first stellar populations may also have produced more light for a given amount of mass. A simulation calibrated mainly on nearby systems could then underpredict the brightness of distant ones, even if its dark matter framework remains sound. This is why unexpectedly luminous galaxies do not immediately reveal a new kind of dark matter. Dark matter determines where and when gas can collapse, but the telescope mostly records light from ordinary matter after that collapse has already begun. The observations can pressure assumptions about dark matter halos, yet they do not directly identify a replacement. A true crisis would require something more demanding. Researchers would need many securely confirmed objects whose stellar masses, intrinsic brightness, and abundance remained extremely improbable after lensing, dust, emission lines, and selection effects were accounted for. Those objects would also need to occupy halos that the standard initial conditions almost never produce at the relevant cosmic age. One striking galaxy would not be enough. Even several unusual systems might still live in the far edge of a probability distribution. The conflict becomes foundational only when the entire population refuses to fit. The broader framework also carries evidence from places far removed from early galaxy surveys. The cosmic microwave background preserves a pattern from the young universe that strongly constrains its initial conditions and matter content. Large-scale structure shows how galaxies and clusters are arranged across immense distances. The measured expansion of space, along with the observed abundance of the lightest elements, provides additional independent tests. Any proposed replacement must explain these successes, as well as the new Webb observations. It cannot solve one tension by discarding every other agreement. That does not make the existing model untouchable. Scientific frameworks survive by exposing their weakest assumptions to better measurements. Some parts will be refined, others may be replaced. The contest is between improved data, more realistic ordinary matter physics, and genuinely new cosmological ingredients. Current observations have not yet decided which possibility will carry the most weight. A weak assumption can fail without the whole framework falling. The black hole universe idea begins with a temptation that appears whenever several cosmic anomalies seem to point in the same direction. An unexpectedly developed galaxy appears near the beginning of cosmic history. A disputed study reports that spiral galaxies may not turn equally often in both apparent directions. The beginning of the cosmos resembles a singular state, while black holes are also associated with singularities in classical equations. Placed beside one another, these facts can feel like parts of a single hidden explanation. Proximity inside a story, however, is not evidence of a physical connection. The first claim concerns the apparent winding directions of spiral galaxies. When astronomers observe a spiral system face-on, its arms may seem to curve clockwise or counterclockwise from our viewpoint. Researchers can classify thousands of images and compare how often each direction appears. In a perfectly balanced sample, the two apparent orientations should occur in roughly equal numbers. Some analyses have reported a small imbalance across parts of the sky. If such a pattern were real, persistent, and independently confirmed, it could suggest that the cosmos contains a preferred direction. That would matter because modern cosmology rests partly on the cosmological principle. This principle assumes that, on sufficiently large scales, matter is distributed in broadly similar ways, regardless of where an observer looks. Isotropy describes the related expectation that no direction across the sky is fundamentally special. A genuine cosmic axis would place pressure on that assumption. The reported asymmetries remain disputed. A galaxy tilted toward the observer can be difficult to classify correctly. Faint spiral arms may disappear into noise, while dust can hide part of the structure. Image processing choices can change how clearly the winding pattern appears. Human classification and automated systems may also carry subtle preferences. A survey covering one region of the sky may not be directly comparable with another survey using different instruments and calibration methods. Even the way a sample is selected can produce an imbalance that was never present in the full population. For these reasons, a possible pattern must survive repeated tests using independent data before it can support a claim about cosmic rotation or direction. The evidence currently falls far short of proving that the entire cosmos turns around one hidden axis. The black hole universe proposal reaches much farther. In some theoretical models, gravitational collapse inside a parent cosmos could create a new expanding region beyond the black hole's interior. From inside that region, the expansion might resemble a new cosmic beginning. The appeal is easy to understand. A black hole draws matter inward, while our observable cosmos appears to have expanded from an extremely dense early state. The two processes can look like reverse sides of one mathematical structure. Resemblance alone does not establish ancestry. Two equations can share features without describing the same physical event. No telescope has observed a newborn cosmos emerging inside a black hole. No signal from beyond an event horizon has revealed such an interior. From the viewpoint of a distant observer, matter approaching an event horizon appears to slow and fade. Its light becomes weaker and shifts toward longer wavelengths. The object never seems to cross the boundary in the ordinary way seen from far away. Close to that limit, familiar descriptions of time and distance become unreliable. Beyond it, no light returns to report what occurred. The exterior grows quiet. The interior remains hidden, not because it is merely dark, but because the causal structure of space-time prevents information from escaping. That silence leaves room for theory, but it does not provide confirmation. One attempt to avoid an infinitely compressed beginning comes from Einstein-Cartan gravity. This extension of general relativity introduces torsion, a possible twisting property of spacetime associated with the spin of particles. Under extreme density, torsion may create a repulsive effect strong enough to prevent matter from collapsing into an infinite singularity. Instead of ending at an impossible point, collapse could reach a minimum size and rebound. Some models describe this as a cosmological bounce. The idea replaces a sharp beginning with a transition from contraction to expansion. It is mathematically interesting because it offers a route around one of classical gravity's deepest problems. It remains one possible extension rather than an observed description of reality. Other theories also remove singularities through different mechanisms. A successful proposal must do more than produce an elegant bounce. It must explain why the cosmos has its measured matter, distribution, expansion history, background radiation, and pattern of large-scale structure. It must also generate predictions that differ clearly from conventional cosmology. Without a unique observational signature, several theories can describe the same known facts while remaining impossible to distinguish. The early galaxies do not currently supply that signature. Their brightness may reveal unexpected star formation efficiency, unusual stellar populations, measurement bias, or missing ordinary matter physics. None of those possibilities requires birth inside a black hole. The disputed galaxy spin results also provide no demonstrated causal link to early structure formation. Combining both puzzles may create an appealing narrative, yet the physical bridge between them has not been established. Radical ideas deserve attention when they sharpen questions and lead to measurable consequences. They become strong science only when observations can place them at risk. A theory that can explain any possible result has explained very little. The black hole universe remains a compelling possibility at the edge of current knowledge, not a conclusion written into the sky. Testable predictions, not conceptual resemblance, decide whether a radical idea belongs to nature. The boundary of the observable universe keeps moving each time Webb reveals a source beyond the previous record. One future exposure may contain another faint point whose light began traveling even closer to the beginning of cosmic history. At first, it may appear as only a slight infrared glow against the background. After careful measurements, that glow could become the earliest confirmed galaxy yet observed. The record itself would probably survive only until the next deeper survey. Seeing farther is no longer the only goal. Astronomers must also understand what each distant source actually contains. A bright point may be dominated by massive stars, glowing gas, dust, a feeding black hole, or magnification from foreground matter. Each possibility changes the physical story hidden behind the same image. Spectroscopy remains essential because colors alone cannot reliably separate all these effects. By dividing incoming radiation into wavelengths, researchers can identify the features produced by different atoms and physical environments. Those patterns can reveal whether the energy mainly comes from young stars or from material falling toward a central black hole. They can also show how strongly intervening hydrogen has altered the signal. Better spectra will refine the distance, chemical composition, temperature, and motion of the gas. Stellar mass requires equal caution. Luminosity can make a young system appear far heavier than it really is. Researchers must estimate the age and type of its stellar population before converting observed output into mass. A short burst containing many high-mass stars produces far more radiation than an older population built from the same amount of material. dust can hide part of that energy, while strong emission lines can add brightness to particular filters. Lensing magnification may increase the observed signal without changing anything inside the source itself. Each uncertainty must be measured before a galaxy can become a serious test of cosmology. Chemical abundances provide another path into the past. Nitrogen, carbon, oxygen, and other elements carry evidence of what earlier stars did before the recorded light escaped. A strong enrichment pattern would suggest that several steps had already occurred. Stars formed from simple gas. They transform part of that gas through nuclear reactions. They release the altered material through winds or explosive deaths. New stars then developed from the enriched mixture. Confirming this sequence within the first few 100 million years would place firm limits on how quickly stellar generations could succeed one another. A faint spectrum can therefore preserve more than distance. It can contain the remains of suns that no longer existed when the photons began crossing space. Individual sources will never settle the question alone. Larger survey volumes are needed to discover how common these objects really are. A rare galaxy can appear naturally in an enormous cosmos, even when simulations predict that such systems should be unusual. 10 or 20 isolated surprises may still come from surveys designed to find the brightest extremes. A representative sample must include less dramatic systems and account for those too faint to detect directly. Only then can researchers measure the true number density of luminous early galaxies. That distribution can be compared with simulations rather than with intuition. The same principle applies to distant clusters. Lensing maps reveal how much matter has collected into a region and how centrally concentrated it has become. Galaxy counts measure the visible members. X-ray observations, where possible, can trace extremely hot gas filling the space between them. Together, these measurements test structure growth on a much larger scale than one compact galaxy. If early galaxies prove common, while massive clusters remain rare, the tension may lie mainly in the efficiency of star formation. If both appear in unexpectedly large numbers, the pressure on the broader growth history becomes stronger. The evidence could still support the existing cosmological framework with revised ordinary matter physics. Gas may have cooled faster in primordial halos. Feedback may have removed less material than earlier simulations assumed. The first stellar populations may have generated more light and heavier elements within shorter intervals. Improving these details could bring the predicted and observed populations into agreement. A different outcome remains possible. Well-confirmed masses and abundances may continue to exceed what the standard initial conditions can comfortably produce. Persistent population-level conflicts could point toward altered dark matter behavior, different early conditions, or another missing cosmological ingredient. That conclusion would require more than a few dramatic discoveries. It would need independent measurements that remain inconsistent after every conventional explanation has been tested. No observation described here demonstrates that the universe exists inside a black hole. No disputed spin pattern currently establishes a preferred cosmic axis. Those possibilities remain theoretical ideas rather than conclusions supported by the early galaxy evidence. Uncertainty is not a weakness in this process. It marks the exact place where observation has advanced beyond the precision of existing explanations. In a future Webb exposure, another group of ancient photons may strike the telescope's segmented mirror. They will arrive without labels stating whether they support refinement or revolution. The instrument will simply collect them. A spectrum will separate their wavelengths. Researchers will compare the resulting pattern with models, simulations, and other observations. Some assumptions may survive. Others may have to change. The light itself delivers no verdict. It only records what the cosmos had already created. Human models are maps drawn from the territory that observations allow us to see. Each deeper measurement reduces the blank space near their edges. The universe does not owe those maps simplicity. At every moving boundary, explanation must become more precise.